Hi, everyone. It's my great pleasure to introduce our keynote speaker today. Johannes Bale is a staff research scientist at Google. Johannes received their doctoral degree at RWTH Aachen University in 2012. This was followed by a collaboration with Javier Portilla in Madrid and a postdoctoral fellowship at New York University with Aero P. Simoncelli, studying the relationship between perception and image statistics. While there, Johannes pioneered the use of variational Bayesian models and deep learning techniques for end-to-end optimized image compression. Johannes joined Google in 2017 to continue working on this line of research. Johannes has served as a reviewer for numerous publications in both machine learning and image processing. They have been active as a co-organizer of the annual workshop and challenge on learned image compression since 2018 and on the program committee for data compression conference since 2022. Please give Johannes a warm welcome.
Thank you. Yeah, so this talk is about learned image compression. And I want to start with this example here. So in case you don't know about learned compression, this is a result that we got in one of our first models that we worked on in 2017. And what really struck me back then was the way that these learned compressors adapt to the data, to the source. And in particular, if you compare the reconstruction here with the reconstructions you get from traditional coders like JPEG, JPEG 2000, you can see that they're essentially free of artifacts. So you have a rate constraint, you do lose detail, but somehow these compressors learn what an image looks like, and they reconstruct images that are plausible. Whereas traditional methods, you can see what type of transform they're using in the way that they show artifacts. And in particular, if you take a look at this contour up here, what really surprised me was that there's this little corner cut out of that contour, and the rate isn't enough to represent that in the bit stream. But somehow the model kind of made up a contour that makes sense in this context. And so that is when we realized that there's really something special about the way that these models work. Machine learning really has kind of revolutionized a lot of fields, and it also has changed some of the things that we can do in compression. In particular, it's very data-driven. So it's very easy to adapt it, both to types of sources. So in the best case, if you want to train a compression model for a different type of source, you change the training data in the simplest case, and you will get an adapted compressor for that type of data. And the same is true for how we measure success in terms of the reconstruction. How do we measure errors? So we can plug in different types of error metrics, and this is kind of what the talk here is about. We can do a lot better job at emulating human perception. So first, I'm going to talk a bit about learned image compression, what it is, sort of give a quick recap of that. Then I'm going to talk about distortion, which is, I think, the sort of most common way to frame how good is an image reconstruction. But I want to expand a bit on that and also talk about what I call realism. And at the end, I'm going to talk about perceptual spaces, which is a concept that applies to both of them. So I probably don't need to explain this diagram in very much detail. I think everyone here knows what JPEG is. So we have an image X here. We subject it to the DCT. We do quantization. We do entropy coding. For the reconstruction side, we use the inverse DCT. And then we can quantify the performance of this model, both in terms of rate and in terms of distortion. If you ask the question like, why do we actually use the DCT and not something else? Well, it goes all the way back to the 70s, where we were conceptualizing images as Gaussians, and under that assumption, the decorrelating transform is the KLT, and it's optimal in that case. So if we make certain assumptions, we can prove optimality, and the DCT just happens to be a really fast approximation of this KLT. So that is why it became really popular, and we're still using variants of it today. But of course, images are not really Gaussians. So we cannot be sure that the DCT or KLT is actually doing the best possible thing here. And it's actually very likely that the optimal transform that we could use is actually a nonlinear transform. And this is where artificial neural networks come in, because they are universal function approximators. So if we can train them, then we can potentially approximate the RD optimal transforms with those networks. So this is the adapted block diagram for what we did in 2017. So now, instead of having DCT and inverse DCT, we have two neural networks. Because neural networks, they subsume companding or compression, right? So we can, without loss of generality, just use a uniform quantizer. We don't need to worry about dead zones or anything like that. And then we just used arithmetic coding for coding the quantized coefficients. Now that raises the question, we have a bunch of parameters here. So both the analysis and the synthesis transforms are networks with parameters. Also, the entropy model has parameters. How do we get these parameters? And so we follow an approach that is very common now in deep learning, machine learning. We write down a loss function. Here the loss function is the Lagrangian between rate and distortion, right? So in this case, we use mean squared error. So we have an expectation over the image of a squared error, and here we have a cross entropy term. And we can write it all out so that it becomes visible what the parameters are. So we expand this, and now we have the transforms here, a quantizer, and then the cross entropy term, and here we have both transforms, right? So now we have a function that is the loss function that is a function of all these parameters, and we use stochastic gradient descent to optimize this loss function. And stochastic gradient descent is different from gradient descent in the sense that we're using only small batches of samples in each step. So we don't have a very large batch size. We go to very small batch sizes, and that works because we can do a Monte Carlo approximation of the gradients. So here in this equivalence, we can just exchange the gradient with the expectation because they're both linear operations. So this is all borrowed from machine learning, deep learning. And lastly, we have tools there as well that help us take those derivatives. You can imagine that the derivatives are analytically very complex. And so we have toolkits that allow us to take these symbolic differences. Now there's one problem, which is the quantizer. So for stochastic gradient descent, we need gradients. We need to take the derivatives. And since we have quantizers in that loss function, now we're going to run into trouble at the point where we try to take the derivative of those, because the derivative is going to be 0, except in singular points where it's infinite. So that's not a useful gradient that we could use for optimization. So the approach we took here was to transition from uniform quantization to dither quantization. And dither quantization has the nice property that for purposes of the conditional distributions and the expected value, we can just replace it with an additive uniform noise. And that gives us the same computation effectively, if we're not trying to actually code it. And it is differentiable. So that allows us, going to this proxy RD loss, which doesn't use quantization but dithering. That allows us to actually optimize the system. There's a technique that has been developed recently that interpolates between quantization and dithering, which is also very nice, and that's allows us to control this a little bit better now even. So what does this look like if we actually apply this to some source? So this is a visualization of a two-dimensional source. We have, it's kind of a ridge shape like a banana here. So we have a lot of probability mass here, and then out here there's almost no probability mass. And what we did here was train a linear transform coder with this paradigm. So linear transform coder is essentially a lattice coder, as you can see here. So we have the lines represent the quantization boundaries, and the dots represent the reconstruction values for the respective quantization bins. And so you can see that the transform kind of adapts to the source somewhat, because it approaches the sort of both fleeting angles. But of course, it's constrained in the way that it can sort of break up the space. And we get a certain performance here. So we recorded the value of the Lagrangian as an average over samples from this source. Now, if we do nonlinear transform coding, you can see that it's still a lattice. So we still have a rectangular lattice because we're doing scalar quantization in the transform domain. But it's now a warped lattice. And so that's due to the nonlinearity of the transforms. And you can see that that adapts to the source a lot better. Now we have like one dimension here that essentially goes along the ridge and another dimension that goes across the ridge. And so this type of adaptation is the same adaptation that we saw in the image in the beginning, where it adapts to the shape of the source distribution. And so comparing that with a rate constrained vector quantizer, we can actually see that they get very close. So if you believe me that this vector quantizer is somewhere close to the optimum, you can see that the difference in terms of performance is not that much. So by allowing it to warp the space in a nonlinear way, we actually get much better performance out of it. So over the last couple of years, there had been a couple of limitations from the first instance of this type of model. One was that we had only one model per rate distortion operating point. So as you can appreciate in the loss function, we have to set this lambda, right? And so if we train for this lambda, we get one model that compresses for this rate distortion trade-off. And then if we wanted to have a different trade-off, we needed to set a different lambda, we get a new model. So this has been addressed in the meantime. And then also in terms of PSNR, we were better than JPEG 2000 at the time, but we were not competitive with more state-of-the-art methods. And there we've also caught up. So we're in a roughly the same ballpark, and most of it is because we introduced better entropy modeling. So many of the improvements come from a model that we call hyperprior model, which is essentially a forward adaptive entropy coding model, where you take the latents, you extract some information from those, again with a neural network. That gives you a representation, and there's some extra information that we send first. And then this information is decoded again with neural networks that predict the distribution of the actual coefficients. So this is an example of forward adaptive entropy coding. You can also do neural backward adaptation. So there's multiple works now in that direction where people experiment with different types of entropy models. And you can see the progression here. So we started somewhere. So this is JPEG. We started down here in 2017. Then we introduced the forward adaptive entropy model. And then here we started combining forward and backward adaptation. And now there's a number of different models that all experiment with this, with improved entropy coding, improved transforms, and so on. So we're now relatively close. We're in sort of the same ballpark as some of the state-of-the-art intra-codecs. So one big question, though, is still computational complexity. So typically we have a different trade-off between encoder and decoder, right? Because we have transfer encoder that is now much more complex than a DCT. We tend to have big part of the complexity in the encoder in the network, and then also in the decoder. So encoder and decoder complexity are typically kind of similar, whereas in hybrid coding, we have a much more complex encoder. But we can do some comparisons. So we can look at a slice here. So if we look at all the models here that average to a certain number of bits per pixel, I think 0.5 here, then we can make a new plot and look at the distortion that they arrive at versus the number of floating point operations that they use. And so now we can see sort of the 2017 model was relatively cheap, still much more expensive than traditional coders. But then we can see that there's sort of a trade-off emerging, right? And now we're in this phase where we're starting to trade off complexity with more sophisticated ways of entropy coding and so on. David Minin has given a lot more detail in this direction in his ICIP 2021 keynote. So I'm not going to go into a lot of detail here, but that's definitely one of the open questions that is still seeing a lot of active research. And so what I'm trying to focus on in this talk is subjective image quality, because we haven't really, we've seen that some of the results look really compelling, but we haven't really understood sort of what are the trade-offs here completely. And one of the early results that we had was comparing a network that is optimized for squared error versus a network that is optimized for MSSIM. So here we're doing a comparison between two images that were compressed with different compressors. Both happen to have the same bit rate. And now you can compare those two reconstructions. And I don't know how well you can see it, but you should be able to see that with MSSIM, there's a lot more detail in the face and in the texture here. And that is because the MSSIM coder moves bits from the background into those areas. So it affects the bit rate allocation. And we see the same here. So here's a comparable example. Again, this is optimized for mean squared error. And then this one is optimized for MSSIM. Here you should focus on the text in the center and the grass texture. So there, when we go to MSSIM, a lot of the bits are moved away from the text and into the grass texture. And that's because MSSIM models contrast masking. So basically, mean squared error will highly penalize errors here because we have a wide dynamic range of pixel values. Here is white to black, whereas the grass is low contrast, right? And so MSE will penalize this a lot, but deviations here are not penalized much, and MSSIM compensates for that. So that's why we're seeing that bits are being moved around. And so an interesting observation here is that the rate allocation decisions are not explicit. They're essentially amortized into the network, and we only need to apply like a learning signal during training to tell the network, where do we penalize distortions? And so we don't need to have a distortion metric that is fast, or we don't need to have a distortion metric that can be evaluated on single blocks. We have a lot fewer constraints in terms of what distortion metrics we can use. I wrote here we can use perceptual models rather than distortion metrics, and so we can actually generalize beyond distortion metrics. What do I mean by perceptual models? Well, we have image quality assessment models, and these are all models that are trying to emulate humans on certain tasks. Like we can show an image, we can ask, does that image look realistic? We can show two images, ask, do they look the same? So there's a number of different ways we can query humans for image quality assessments. And I think this list here is not exhaustive, but there's, for example, we can talk about two alternative forced choice. So we basically ask the humans to give a binary answer, or we can talk about mean opinion scores, so we can ask on a scale between 1 and 5, how good does this image look, and etc. What I want to focus on here is a distinction between showing two images and comparing them, so a full reference metric scenario, or I would call this distortion. That versus a scenario where you show one image, and so you have a no reference scenario, and that is where I would call it realism, right? We're asking if this image is realistic without a reference. So first, let me talk a bit about distortion. So what do we need if we want to optimize a compression model for distortion? Well, first of all, we want it to be a good model, right? So we wanted to predict human ratings well. We want it to be differentiable and well-defined. So we need it to be differentiable because we use stochastic gradient descent. We want some well-definedness. For example, we want to have it be a minimum if we're putting the same image in twice. And then we want it to generalize across different images and types of distortions. So what does that mean, generalize? So here's an example, an experiment that kind of demonstrates what this means. So a lot of distortion metrics actually are really bad for optimization. They have blind spots. And this paper here, people did an experiment where they just wanted to see how well can you optimize for a given metric. So this doesn't even include any compression. All they did was they took an image that they initialized to noise, so like up here in the corner, and then they iterated on this image, optimized it to minimize the distortion between it and some reference image. So in this case, it was like an image of a church. So in these images here are the results for different types of metrics. And this is quite surprising that not all of them actually give you something back that even remotely looks like the original image. So some of them produce essentially, it looks like garbage. They produce some stuff, and apparently the metric says, well, this looks close enough to the original image. What does that mean? Why do they need to generalize? And the difference here is that we're optimizing for it rather than just evaluating it. So if we do quality assessment, a lot of these metrics are used for quality assessment after the fact, after we have our artifacts in the image. And so when we evaluate them on a particular type of distribution, which is the joint distribution of natural images. and the distribution of distorted images, right? And so this distribution of distorted images will only contain a certain type of artifact. So we're evaluating it in a certain part of the space where the type of artifact is determined by our compression scheme. So if we train a model, then we need to expand that domain, right? Because a neural network, as it learns to produce reconstructions, it will explore the space. It will start going in all kinds of directions and produce reconstructions that could be whatever. And we need the distortion metric to tell us, okay, you need to go in this direction. And that is not the case for a lot of these metrics here. Why do we find out about that now? Well, it's because we also have blind spots in our data sets. So, for example, the TID, Live, and CSIQ data sets, very popular, very well collected data. Show images to humans, you collect their responses about similarity. It's all great, but they don't contain certain types of distortions. So we only evaluate the distortion metric, again, on these types of distortions. There's now a couple more data sets cropping up that actually have different types of distortions, like these type of structural distortions here, where you have Bohr pinks and so on. But we're still quite limited on data sets that are good in actually evaluating distortion metrics. So it's not looking that great right now. We need a lot more work on good distortion metrics. And if we want to use learned compression and optimize these compressors for such metrics, we need to be aware that neural networks will cheat. They will go to parts in the space where the distortion metric is not giving useful answers. Okay, so how can realism potentially help with this? So here I'm looking at no reference metrics, which some of you might be familiar with. And I'm trying to give it sort of a more idealized notion. And I'm connecting with the notation that is used in a paper down here. So in an idealized way, we could say a critic, a human or a model that tries to determine if an image is realistic. You could say it takes that image, it has a model of the natural image distribution, that's PX up here, and it has a model of the distribution of reconstructed images or distorted images. And then it could do a likelihood ratio test between them, right? It could look at the likelihoods of both, compare them, and then take a decision based on that. So in a realism type of scenario, in a no reference metric, the critic here actually needs to learn a model of the distribution of artifacts. So that is actually what a lot of no reference metrics do. They are designed to detect a particular source of artifacts. So for example, there are no reference metrics that detect block artifacts specifically. Super useful for hybrid coding, right? Because you know that the artifacts will have a certain type, and you can detect that. You can detect how likely it is that you see an artifact. So that means here also we have a generalization problem. But there has been, we have a new twist on this type of model actually through generative adversarial networks. And these GANs take sort of this type of decision sort of to the next level, in the sense that they make it an optimization game. So we have a game between a critic that tries to guess if an image is fake or real, and a generative model that produces the images down here. So essentially, the generator tries to produce images that look natural, that fool the critic, and the critic learns to classify images into real or fake, and thereby it's learning this likelihood ratio in different parts of the space. So this is also how some people define realism. We take this likelihood ratio, and if we take the expectation over the image distribution, now we have a divergence, right? We have a divergence between two distributions, the natural image distribution and the distribution of the degraded images. So for example, if we take this notation is due to Novocene, so they have formalized this and expanded it to F divergences. So if we replace F here with R log R, then that becomes the Kullback-Leibler divergence, but we can also make other choices here. The bottom line is that if we participate in this adversarial game during training, that is one way to achieve better realism. So we can achieve better realism and not necessarily need to rely on fixed no reference metrics. So why do we want realism and not distortion? Or why do we still want distortion if we have realism? Why are both necessary? You know, do we maybe just need one? So this is actually a good example. So we're trying to compress an image, and now we have different models that are trained for either rate and distortion, or rate and realism, or rate and both. So if we train for rate and distortion, we're likely to get a reconstruction kind of like this. So we have a rate constraint, so that means we cannot send all of the information in the image. So something has to be cut, and that typically means that we get a slightly blurry reconstruction because the high frequency detail is going to be lost. But you can also say, you know, you can detect this is not a realistic image because it's blurry all over, right? So if you just see this image and you ask a human, is this a realistic image? It might just be very blurry, so they might say no. What if we only train for rate and realism? So here, we might actually satisfy the requirement with any image, right? So we can have a decoder that produces just any realistic looking image, and the realism constraint will be happy. But of course, it will not have anything to do with the original, right? So this is also not what we want. So we need both, but both things are also kind of at odds with each other. So here, we're kind of trying to train for all of them, and now we hope to get a reconstruction that resembles the original, but also has some additional detail that makes it look more realistic. There's a very nice paper that was published at CVPR in 2019 that actually shows that there is a three-way trade-off. So for any given model that has a constraint, like a rate constraint, we cannot be perfect in all three of them. So we cannot reach, so that there's a three-way trade-off between rate, distortion, and realism. So this is, you know, another type of model that has become popular now, where we have the same setup as before, but now instead of training for rate and distortion, we actually add another adversarial loss that approximates, you know, this divergence between the natural image distribution and the reconstructions. It approximates because it's not, it's unfortunately not a one-to-one correspondence, so there's an approximate relationship between these things. Okay, and so here I'm going to show some results of a model like this. So I think you can see it here. This model produces some texture here that is not in the reconstructions from the distortion-only models. You might also notice that this texture, so it looks more realistic, but it's not the same texture as in the original, right? So it hallucinates some detail that just sort of statistically looks like it's in the right place. And that's because it still has to work with the rate constraint, right? Like it can't send the information pertaining to this instance of the texture. It kind of has to make up some of the detail. And we see the same in different images. Here again we have, I think this is the original, and then here we have a reconstruction with this adversarial model. Whereas here in the distortion only model, we get just mostly blurring, especially in the areas that are low contrast, because this is a model that is optimized for mean squared error. So we did human studies on this model, and it is generally preferred. So humans prefer the reconstructions that have been optimized with realism. This is showing too much information. I'm just going to go a bit faster here. We do have some cases which we would consider failure cases, and that is particularly in the situations where humans are extremely sensitive. So for example, in an image like this one, the face covers the entire image, so it's more like a global structure, and there we don't have a problem. But if we look at images like this, where we have relatively small faces, humans are still very attentive to these details, right? More so than attentive to the details up here, even though it's the same scale, right? Humans are extremely sensitive to faces, and so the model here treats it the same as any other texture, and it just produces something that is kind of flesh-like. So that's not ideal for your vacation photos, right? So why is this? Because we're applying these realism and distortion constraints in a pixel representation, right? So we're trying to match distributions of pixels. And human vision doesn't really work in pixels, right? We have a lot of processing going on, and many of the features that we attend to cannot be sort of adequately captured in a pixel space. And this leads me to the fourth part, where I'm going to talk about perceptual spaces. So as I just said, the brain needs to process the information that's coming into its senses, right? And for the most part, that means we need to filter out information, because we have so many, we have millions of cells in our eyes alone, and like processing all of that consciously is not possible, right? So we need to rely on a machinery that pre-processes all of this and filters out the irrelevant bits. And that happens on all kinds of levels. So for example, it happens in the eye itself, because we only have sensitivity to certain wavelengths, right? It happens in parts of the visual system that can compute things automatically, pre-attentively. So we might have masking effects. If there is a certain amount of stuff in a certain area, you don't see other stuff. It just kind of gets masked. And then we can also have, influence from cognition. So where we direct our attention makes a big difference in terms of what we perceive. So low-level example would be the fact that we have 3 or 4, depending on how you count, different types of photoreceptors in the eye. And our eyes are exposed to all these wavelengths and power spectral mixtures of wavelengths, but we don't perceive all of that. We just see a projection. We see a response of these 4 different types of cells to this mixture of wavelengths, right? And so that is one way in which we use the physiology to actually filter out information. And this is really easy to forget about, because we have already built this kind of stuff into all our tech, right? So displays, cameras, even illumination now with LED lights, we wouldn't be able to have this kind of tech if we were actually able to distinguish all these different types of wavelength spectra. And then here we have an example from the other end. So here, this is a more cognitive example, where if you look at these 2 images on first glance, maybe you think they're the same. But then as you direct your attention to different parts of it and you scrutinize parts of the image, you can actually appreciate that there is a difference. And so that is one example where cognition has an effect on perception, right? So it's a top-down kind of thing, and that's, of course, even harder to model than the low-level stuff. So how do we deal with this? So many image quality assessment models actually try to emulate this in a way. So they use proxy representations, which is essentially another transform. We're going from a stimulus space or a signal space. We're taking, we're thinking of our image, our audio signal as a vector in a space, and we're applying a transformation that goes into a different space. And we might want to call it perceptual space if it satisfies certain requirements, right? We would like to have that if we take a distance between 2 points and then take the distance of the transformed points, we would like that distance to correspond to human notions of how similar these stimuli are, right? So ideally, points that have a similar distance in this space look roughly similar to the same amount. Or we could also frame it in terms of just noticeable differences. So if you think about the set of stimuli that are just noticeably different from that point in the center. In a stimulus space, it might be some weird curve. It might be an ellipsoid. In the perceptual space, we would love to have it be a circle, right, or a sphere, because we would like to be able to make predictions in that space with simple metrics. So the goal would then be to expand this flow chart, and instead of measuring our distortion and realism directly in the signal space, we first apply a transformation and then measure those errors here. So one early example of this is from the 1940s, where McAdam ran an experiment, and they showed humans these screens of flat colors, and then they varied the colors and tried to assess how easy is it for people to distinguish 2 colors. And it turns out that if you draw these just noticeable differences as ellipsoids in the chromaticity diagram, you can see that in the green area, we're much less sensitive than in the blue area, for example. And so now we have color spaces, and the design of the color spaces takes this into account. We're trying to design color spaces to make these ellipses into circles. For a more modern example, there was an experiment conducted at MIT in around 2016, where people took an object recognition network. So they trained it on an ImageNet database or something like that. And then they took recordings from cells in the visual system. So they showed images to both, and then looked at what the activations are in the different parts of the visual system, and compared them to the activations in the neural network. And it turns out that there is a correlation. And more specifically, they found that early stages in the visual system correlated with early stages in the object recognition network, and later stages correlated to later stages. So that raises the question, can we maybe use this as a perceptual space? And that's exactly what some work does. So here, one example is LPIPS, which does exactly this. So they train a neural network to do object recognition, and then they treat the activations in certain layers as their perceptual space. So they compare images in those spaces. And so that works remarkably well even for structural distortions like these warpings. Now, here's an experiment that we conducted a while ago, because we asked ourselves, these experiments, we still require a lot of human ratings. We still need to have humans annotate class labels. There's actually also adaptation layers. So sometimes they then fine tune these models on human ratings of quality. So you collect all this data. You still need to ask humans for data, and it can be very expensive, especially if you want to make this scale this bigger. So we asked ourselves, can we come up with a model that doesn't rely on data, that maybe just that gets along without actually asking humans for ratings? And so here we relied on some concepts from computational neuroscience, in particular, the idea of slowness. So this slowness idea is kind of it's an abstraction of how the brain processes information and what information is relevant versus irrelevant. Let me give you more detail on this. So if if you look at a video, right? So this is supposed to be a video. There's a person speaking, and if we think about what are the activations in our brains going to be as we perceive this scene, then if you look at a retinal image, right? So if you look at a particular cell in the retina, it's going to be all over the place, right? Because we look at different things, things move around, there's a bit of jitter. So everything, the retinal image will be very quickly fluctuating over time. If we look at something higher level, so if we look at a part of our brain where we process the facial expression of that person, then those kind of features will be fluctuating a lot slower, right? Because the person has a certain facial expression, independent of how their head is oriented and so on. Like there's a lot of variability that is then filtered out, right? And so the relevant features here, they progress much slower over time. And then if you think about things like object presence, so is there this mirror in the image? That's going to be even slower, right? So we have like a feature hierarchy where the less relevant nuisance features tend to fluctuate very quickly. And the important ones, the semantically relevant features, tend to fluctuate slowly. So we tried to build, so you can appreciate that for image similarity, you compare these two images, they tend to look exactly the same, right? So if you just glance at them, it's very hard to see a difference. But if you take the difference image, you can see here that there is actually quite a bit of difference. So there has been some global motion in there, so we see a lot of the edges. And also there's some motion here in these textures, right? So here we see they look the same, but they're actually different instances of the texture, right? And so these are two frames that were taken within a second of each other, right? And so that's kind of the idea here, that within a short time frame, a lot of things change in the image, but mostly they're not perceptible. So we built a model. We did an experiment where we learned a representation of an image, where we tried to formalize this idea, and we built it on top of information theoretic ideas. So we looked at videos. We took some videos from YouTube, public ones, and we extracted patches of neighboring frames neighboring in time, right? And so we try to construct a representation that only contains the information that is present in both, but not the information that's particular to one of the frames. So you can set up a learning objective. Don't want to go into too much detail here because that takes a long time to get into detail with. But essentially there's a neural network that takes an image and produces a representation in some other vector space. And then there is another network that takes both images and produces a representation. So this joint encoder here, as we call it, is only necessary during training. And then once we're done training, we're going to use this marginal encoder here. So that is going to be our transform that's going from an image to a perceptual space. I have a visual explanation for how this training works in a second. So the architecture of this encoder looks like this. So we have a front end that is a multi-scale filter bank. Multi-scale processing is very, very helpful, and it also has its correlates in the visual system. And then we have neural networks here that sort of are stacked on top of each other and produce a representation. It's a multi-scale representation. So these are tensors, and essentially it's like a combination of a neural, of a ConvNet with a multi-scale filter bank. And this whole thing is trained with a contrastive loss. So what that means in a nutshell is we're feeding the model with examples of frames that are from neighboring, examples of patches that are from neighboring frames. So for example, this pair here. And we have a loss function that encourages the representation of both of these images to get closer together. Then we take one of those images and we grab a random other frame and we combine those into a pair, and then we encourage the model to produce representations that are sort of repulsed, that are further apart. That's where the name comes from, like contrastive learning. We're giving negative and positive examples and telling the network to adjust the representation accordingly. And then, so once we're done training, we take this encoder, and then we can define our distortion and our realism in that space rather than directly operating on pixel values. And we find that, surprisingly, this actually gets competitive results on this BA-PPS data set where we have structural distortions, and we are, we're predicting human raters with an accuracy that's very close to this other model that I showed earlier that is based on classifiers. So we can produce models that are, give perceptual ratings that emulate perceptual ratings without actually ever using a human rating. And so this is where my talk ends. I think I'm good in time. We have maybe time for a couple questions. To wrap up, we need generalization. We need better metrics for optimizing compression models, and that will be, an area where we will need to see a lot more work. Some of the ingredients might be that, we want to trade off between distortion and realism. It's important to ask not just point-wise questions, do these images look the same, but we also want to ask people, do they look realistic? That is, by the way, something that has been adopted already a long time ago in audio and speech processing, right? There, we don't just ask, does this sound the same, but we actually ask people, is this understandable? Can you understand the speech, and so on. So we want to ask more sophisticated questions about the quality of the reconstruction. And I believe that some of this will be also helped by developing better perceptual spaces. And to that end, we might want to shift from things like color spaces where we model psychophysics experiments, or we take models of cells and then try to transfer them into a perceptual metric. Rather than that, maybe we want to abstract a bit and model brain behavior, right? So we want to ask the question, what is the brain learning, and can we make a machine learn that, and then hopefully get a representation that is comparable. So I want to thank my collaborators. This has been a summary of a lot of work with different people. They're not even all listed here. And here are some references that you might want to look into.